In question 1, we've got the Venn diagram here showing the three events A, B, and C with the associated probabilities. And in part A, we need to find the probability of A. Well, the event A is what I'm shading here in red. So obviously, we can say that the probability of event A happening is simply the 0.13 plus the 0.25, which gives an answer of 0.38. We are then told that the events B and C are independent, and we need to determine the values of P and Q. Well, we know that if two events are independent, this simply means that the probability of their intersection is simply the product of their individual probabilities. So looking at the Venn diagram here, the probability of B intersection C is the 0.3. The probability of B is the sum of these three probabilities, and the probability of C is simply the 0.3 plus P. So this leads to 0.3, the probability of the intersection, being equal to the 0.25 plus the 0.05 plus the 0.3, which is the probability of B, times the probability of C, which is 0.3 plus P, which leads to 0.3 is equal to 0.6 times the 0.3 plus P. If I divide both sides by 0.6, I get 0.5 is equal to 0.3 plus P, and therefore we get that P is 0.2. Now, to proceed in finding Q, we can simply consider that the sum of all probabilities here should be equal to 1, which means that we've got 0.13 plus 0.25 plus 0.05 plus the 0.3 plus the 0.2, which was the value of P, plus the Q is equal to 1. So we get 0.93 plus Q is equal to 1, and therefore Q is equal to 0.07. And in part C, we need to find the probability of A given B dash. So we're looking at conditional probability. We know for sure that we're outside of B, so we could be here, here, or here. And we're wondering what's the probability that we are in A. So the only intersection is that part, the 0.13. Well, we have already found that P is 0.2 and Q is 0.07. So to find the probability of A given B dash, I will simply consider what I have double ticked on my Venn diagram, which is the 0.13, over what I have ticked originally is the probability of B dash, which is the 0.13 plus the 0.07 plus the 0.2, and this gives an answer of 13 out of 40. In question 2, we've got a machine filling packets with sweets, and the 7th of the packets also contain a prize. Now the packets of sweets are placed in boxes with 40 packets of sweets in each box, and the random variable capital T is representing the number of packets of sweets containing a prize. Now we need to state a condition needed for capital T to be modeled through a binomial distribution with parameter n is 40 and p is 1 over 7. Well, if we recall the conditions for a binomial distribution, we know that trials need to be independent. So in this case, packets contain a price independently of each other, or alternatively, we could refer to the idea that the probability of success is constant. So in our case, the probability of a packet containing a price is constant. In any case, the comment should be in context, so we need to be referring to packets and prizes to claim the mark here. Now we've got a box selected at random, and using the binomial distribution specified, we need to find the probability that the box has exactly 6 packets containing a prize. So we are asked to find the probability of T being equal to 6. So I'm going to go on my calculator, I press menu, it's option 7 distributions. I go for option 4 binomial PD and option 2 variable. So my X is 6, my N, the number of trials, is 40, and my P, the probability of success, is 1 over 7. So we press the equal sign and we get 0.1727. In II, we need to find the probability that the box has fewer than 3 packets. So we need to find the probability of T being strictly less than 3, which can be written as a relaxed inequality as the probability of T being less than or equal to 2. The reason we need this is that the calculator is working with cumulative probabilities, so less than or equal. So I'm going to press menu again, option 7, I go down, and it's option 1 binomial CD cumulative distribution. option 2 again. So my x now is 2, the n is 40, the p is the 1 over 7, it's still there. So I press the equal sign and I get 0.0616, which I will store on my A key because I'll be needing this later. So I'm gonna put a small a here to remember that I've stored it on A. Camille's Sweet Shop buys 5 boxes of these sweets, and we need to find the probability that exactly 2 of these 5 boxes have fewer than 3 packets containing a prize. So we are now looking at the number of boxes containing fewer than 3 packets that contain a prize. So I will actually start by defining a new random variable. It's x, which is the number of boxes with fewer than 3 packets that contain a prize. So we will be looking at 5 such boxes. So this is still a binomial random variable. However, the parameter n is 5. And the probability of success is exactly what we found in II above, the 0.0616 ... which remember we have stored on A. And we're trying to find the probability of x being equal to 2. So what I will do, I'll go back to my calculator. It's menu 7 for binomial PD 2 variable. My x is 2, my n is 5, and my p, I will simply recall a, so alpha and a, and this will give an answer of 0.0313. Now Camille claims that the proportion of packets containing a prize is actually less than a seventh. We took a random sample of 110 packets and 9 of them turned out to contain a prize, and we need to use a suitable test to test Camille's claim. Now we need to be stating the hypothesis clearly, and we're using a 5% level of significance. So we start by stating that now the random variable t follows a binomial distribution with parameter n being 110, and the probability of success is p. My null hypothesis says that p is 1 over 7, and my alternative is the Camille's claim, which states that p is actually less than a seventh, and we're working at an alpha level of 0.05. Well, under h naught, which means that if h naught is indeed true, then t follows binomial 110, a seventh. Well, we have observed 9 packets containing a prize, so we need to find the probability of t being less than or equal to 9. Remember, we are inheriting the direction from the alternative, and it's always an inclusive inequality because 9 has been observed. So once more, I go on my calculator, menu 7, go down, option 1, variable, my x is 9, my n is 110, and my p is the 1 over 7. So this will give me the probability, which is 0.0383, which is less than the significance level of 0.05. And therefore we say that this is significant. We reject h naught, and we need to conclude in context there is evidence to support Camille's claim. Now, alternatively, I could have followed the critical region approach, which means that instead of testing the 9 that we have seen, we will find the critical value and therefore the critical region. So essentially, we're solving the probability of t being less than or equal to the critical value c to be less than 0.05. Now, how do we find c? We go on the calculator, we press menu 7, and we go down binomial cd. We will be conducting a search to find the critical value, the value that gives me a probability which is less than 0.05. So I'm gonna go for list. I will put randomly some values, maybe 5, 7, 9, just to investigate on what's happening. I will put my n to be the 110 and my p to be the 1 over 7 and check the probabilities that I get. So we can see that the probabilities are quite small, and I get quite close to 0.05 when x is 9. So I will now investigate 9, 10, and 11. So 9, I will put 10, I'm gonna put 11. I'm looking for a value that will give me a probability which is less than 0.05 and a value that will give me a probability which is greater than 0.05. So let me run this, and I see that the probability of t being less than or equal to 9 is 0.0383, and the probability of t being less than or equal to 10 is 0.0719. Therefore, we conclude that the critical value C is equal to 9 because it's that value that gives you a probability which is less than 0.05. Please note that the examiner wants to see this working to award the marks here, and therefore we conclude that the critical region is any value of t which is less than or equal to 9. So the critical region is t less than or equal to 9. It's the set of values. And since 9, what we have seen is in the critical region, we reject H0, and therefore there is evidence to support Camille's claim. In question 3, we're studying the daily total rainfall x millimeters in Liming for 1987. So this is a question on the large data set. So we've got the data summarized here, and we need to explain how the data will need to be cleaned before Ben can start to calculate statistics such as the mean and the standard deviation. So looking at the frequency table here, we can see the TR here. This is a trace of rainfall, which means it's something which is less than 0.05 millimeters, and we know that this will effectively be treated as 0. So all we need to do is state that the TR will be treated as 0. Now, using all 184 of these values, we've got the summary statistics, the sum of the x and the sum of the squares, and we need to calculate estimates for the mean daily total rainfall and the standard deviation. Well, let's start with the mean. We know that the mean x bar is simply the sum of x over n, which in our case is 390 over 184. Remember, we need to be giving answers to 3 significant figures, so it's 2.12 millimeters because we need to include the units as well. For the standard deviation, we know that the formula says that sigma, the standard deviation, is the square root of the sum of the squares over n minus the sum of the x over n all squared and the square root. So in our case, we're looking at 4,336 over 184 minus the 390 over 184 all squared and all square root. Well, if I plug this on the calculator, I get 4.37, and this is also millimeters. Remember that the standard deviation has the same units as the original variable. Now, Ben suggests using the statistic we calculated in part BI, the mean we calculated, to estimate the annual mean daily total rainfall in Liming for 1987. And using our knowledge from the large dataset, we need to give a reason why this data will not be suitable. Well, we know that the large dataset does not cover a full calendar year. It only goes from May to October, so we cannot calculate the annual mean daily total rainfall for a full year. And in II, we need to state, giving a reason how we would expect the estimate we obtained in BI to differ from the actual annual mean daily total rainfall in Liming for 1987. Well, as we said, the large dataset covers from May to October, so we are not including November to April, which tend to be the wet months, which give more rainfall, and therefore we expect the estimate to be less than the actual mean. In question 4, we've got a study made of adult men from a region A of a country. We found their heights to be normally distributed with a mean of 175.4 centimeters and the standard deviation of 6.8 centimeters. And we need to find the proportion of these men that are taller than 180 centimeters. Well, let me start by defining my random variable x to be the height. And we have been told that x follows normal with mean 175.4 and a standard deviation of 6.8, so the variance is 6.8 squared. We need to find the probability of x being greater than 180, so I'm gonna go on my calculator, I press menu and then 7. It's option 2, normal CD, the normal cumulative distribution. So we know that the lower will be 180 and the upper will be something large and positive. So I will put 10 to the power of 9. My sigma is 6.8 and my mu is 175.4. This will give me the exact probability, which tends to be 0.2494. We then have a student claiming that the mean height of adult men from a different region, region B, is different from the mean height of men from region A. we obtained a random sample of 52 adult men from region B, giving a mean height of 177.2. We are assuming that the standard deviation is still 6.8 centimeters, and we need to use a suitable test to assess the claim, stating the hypothesis clearly and using a 5% level of significance. Well, let's start with the null hypothesis, which says that the mu is still 175.4, what we know for region A, whereas the alternative says that mu is different to 175.4. So we're looking at a two-tailed test here. My alpha level is set at the 5%, and we know that x bar, the mean obtained from the sample, was 177.2, sigma is 6.8, and n, the sample size, is 52. Well, under H naught, which means that if the null hypothesis is indeed true, then the sample mean follows a normal distribution with mean 175.4 and variance 6.8 squared over 52. So we divide by the sample size, and we know that if there is indeed a change, a significant difference from the null hypothesis, is towards the greater than, because we have seen something greater than what we expected. So this means I will be finding the probability of x bar being greater than 177.2. So once more, I'll go on my calculator, I press menu, 7, it's the normal CD. My lower is 177.2. I keep my upper to be something big and positive. My sigma is the square root of 6.8 squared divided by 52. And my mu is 175.4. This gives an answer of 0.0281, which is greater than the 0.025. Notice that I have halved my significance level because this is a two-tailed test. I'm looking both to the left and right of the distribution, so I'm halving the significance level. And since what we have seen is not extreme enough, we haven't seen a probability being less than 0.025, we say not significant, do not reject H naught. And again, we need an interpretation in context. We say no evidence to support the student's claim. Alternatively, we could have followed the critical region approach, so I still have the same null alternative hypothesis. My alpha is 0.05, my sigma is 6.8, and the sample size is 52, and yet the under H naught x bar follows the same distribution as stated already. So when we follow a critical region approach, we need to find the critical values, and here we've got two critical values because it's a two-tailed test. So if I draw my bell-shaped curve here centered at the mean of 175.4, then we're looking at those values C1 and C2 that leave 0.025 on each tail, so on the left and on the right hand side. So essentially we need to solve here the probability of x bar being less than C1 to be equal to 0.025, and the probability of x bar being greater than C2 to be also 0.025. So for the probability of x bar being less than C1, I'm gonna go into menu, I'm gonna choose 7, I go to inverse normal, my area will be 0.025, my sigma will be the square root of 6.8 squared divided by 52. My mu is 175.4. I press the equal sign, and we see that C1 is 173.55. Whereas for the probability of x bar being greater than C2, the first thing I need to do is write this as the probability of x bar being less than C2 to be equal to 0.975. So going back on my calculator, I change the area to 0.975. The rest of the parameters remain the same, and we get 177.25. So C2 is 177.25. These two are the critical values, which means that the critical region is anything between the 173.55 and 177.25. Well, what we have seen is 177.2, so we can see that it doesn't lie within the critical region. And therefore we simply need to state that 177.2 is outside the critical region. This means we are looking at a non-significant result. We do not reject H0, which means that we have no evidence to support the student's claim. In part C, we need to find the p-value for the test in part B. So I will start by giving the definition of the p-value. Well, the p-value is the probability of obtaining a result which is at least as extreme as the one actually observed, assuming that H0 is true. So if we put it simply, if we start by assuming that the null hypothesis is indeed true, what's the probability of seeing what we have seen or something even more extreme? So once again, I will draw my bell-shaped curve. We have seen 177.2, it's on the right hand side, and the tail has left a probability of 0.0281 towards the right tail. However, this being a two-tail test means that the extremity will be assessed by also considering the left tail. So we could have seen something extreme on the left tail, so another 0.0281 on the left tail, which means that the p-value will simply be found by multiplying the 0.0281 by 2, which gives an answer of 0.0563. In question 5, we've got Tissam playing a game. She uses a ball, a cup, and a spinner, and the random variable x represents the number the spinner lands on when it's spun. And we've got the following probability distribution for x, a, b, c, d being probabilities. So how do we play the game? We spin the spinner once to obtain a value for x, and Tissam then stands x centimeters from the cup trying to throw the ball into the cup. Now the event capital S represents the event that Tissam successfully throws the ball into the cup, and we are modeling this game under the assumption that the probability of S given x is simply k over x, where k is a constant, and the probability of S intersection x is the same irrespective of the value of x obtained. Now based on this, we need to show that C is 8 over 5b, and I will start with the conditional probability statement. The probability of S given x is simply the probability of S intersection x is x over the probability of x being x. I will cross multiply to get probability of S given x is equal to x times the probability of x being equal to x is simply the probability of S intersection x is equal to x. So remember that the probability of the intersection is the same whatever the value of x obtained. So if I choose x to be 50, I'm getting the probability of S given x is equal to 50 times the probability of x being equal to 50, and this should be the same as the probability of S given x is equal to 80 times the probability of x being equal to 80. Remember, this holds true simply because the probability of the intersection is the same irrespective of the value of x. So this one is the probability of S intersection x is 50, and the right hand side is the probability of S intersection x is 80. So these two should be the same. Now the probability of S given x is 50 is simply k over 50, using the fact that the probability of S given x is k over x, and the probability of x is 50 is b, which should be equal to k over 80 times c. Well, obviously the k's will cancel out, the 0 with the 0 cancels out, and therefore if we cross multiply, we get 8 over 5 times b is equal to c as required. In B, we need to find the probability distribution of x, so essentially we need to determine the values of a, b, c, and d, and I will follow in exactly the same fashion we employed in A. So I could start by saying the probability of S intersection x is 20 times the probability of x is 20 is equal to the probability of S intersection x is 50 times the probability of x being equal to 50. So we get k over 20 times the probability of x being 20, which is A, to be equal to k over 50 times b. So we can see that the k's cancel out, the zeros cancel out, and we get that A is equal to 2 over 5b. And we can further say that the probability of S intersection X is 100 times the probability of X is 100 is the probability of S intersection X is 50 times the probability of X being 50. So this time we've got K over 100 times D is equal to K over 50 times B. So I will once more cancel out the K's, cancel out the 100 with the 50, leaving me a 2 here, and we get that D is equal to 2B. So I have expressed A, B, and C in terms of B. Well, we know that A, B, C, D are probabilities, and their sum should be equal to 1. So we know that A is 2 over 5B. I will keep B. We have found C to be 8 over 5B, and we have found D to be 2B. So if I add the left-hand side, I get 5B is equal to 1, which means that B is 1 over 5, and therefore A is 2 over 5 times 1 over 5, which gives an answer of 2 over 25. C is equal to 8 over 5 times 1 over 5, which gives an answer of 8 over 25. And D is 2 times 1 over 5, which is 2 over 5. So we have just found the values of A, B, C, and D. And since I've been told to find the probability distribution of X, I will simply draw up a table. These are the possible values for X, and I will simply fill in the associated probabilities. So it's 2 over 25, it's 1 over 5, it's 8 over 25, and 2 over 5, and you can simply check that these add up to 1. Now Nav tries a large number of times to throw the ball into the cup from a distance of 100 centimeters, and he successfully gets the ball in the cup 30% of the time. We need to state, giving a reason why this model of the game is not suitable to describe Nav playing the game for all values of X. Well, if we recall the assumptions that Tissam made, we had that the probability of S given X is 100, so we know that we are throwing from a distance of 100. We have seen from the large number of times that Nav tried this to be giving a probability of 0.3, and we know that this should be equal to K over 100 according to Tissam's model. This means that K turns out to be 30, and if I go to apply this, for example, for the probability of S given X is 20, this should be K over 20, and we have just found K to be 30. So this is giving 30 over 20, which is obviously greater than 1, which is not valid, and therefore we conclude that the model is not suitable. In question 6, we've got a medical researcher studying the number of hours capital T a patient stays in a hospital following a particular operation. We've got the histogram summarizing the results for a random sample of 90 patients shown here. And we need to use the histogram to estimate the probability that we're between 10 and 30. So I will start by identifying the cuts of the classes on the horizontal axis. So we've got 4, 7, 12, and 16. We've been asked to find the probability, estimate the probability that is between 10 and 30. So I could shade the corresponding region on my histogram, and essentially I need to do the shaded area over the total area to obtain an estimate for the probability. I will start by determining the total area, which is simply the sum of the areas of the bars. So this is 4 times 2.5, that's the first bar, plus 3 times 3, the second bar, plus 5 times 4.2, and then we've got 4 times 4, and then we've got the 4 times 3.5, and the last bar has a width of 20 and a height of 1, so that's 20 times 1, which gives an answer of 90, which matches exactly the sample size. And I will now proceed in finding the shaded area, what I have shaded in red on my histogram here. So this is 2 times 4.2, which is the 10 to 12 class here, the bar here. Then from 12 to 16, we've got a width of 4 and a height of 4. And then from 16 to 20, we've got 4 times 3.5. And then from 20 up to 30 is 10 times 1. Well, if I add this up, I get 48.5 0.4, which means that the probability that we are between 10 and 30 is simply the 48.4 over the 90, which correct to three significant figures is 0.538. Notice that if you give an exact answer, you will be penalized. Remember, we are using the histogram to estimate, and if we give an exact answer, we are kind of hinting at this being exact, but we cannot be sure that this is the exact probability. It's based on an estimate because it's derived from the histogram, so we need to give our answer correct to three significant figures. Now, for these 90 patients, the time spent in hospital gave a mean of 14.9 and a standard deviation of 9.3 hours, and Thomas is suggesting a normal distribution with the corresponding parameters, and with reference to the histogram, we need to state giving a reason whether this model could be suitable. Well, we know that the fundamental characteristic of a normal distribution is the symmetric nature of the bell-shaped curve. So looking at the histogram here, we can see that it is not symmetric. We can see that there is a tail towards the right, and therefore we can simply say that the histogram is not symmetric, and therefore the model is not suitable. We then have the suggestion that the frequency polygon based on the histogram be modeled through this curve here, where x is measured in tens of hours and k is a constant, and we need to use algebraic integration to show the given result here. Obviously, I need to use integration by parts here. I will be putting u to be x and v dash to be e to the negative x. So u dash is simply 1, and v is the integral of e to the negative x, which is negative e to the minus x. So the integral from 0 to n of x e to the minus x dx will simply be minus x e to the minus x from 0 up to n minus the integral of 1 times the negative e to the minus x dx from 0 to n. Now if I substitute n, the upper limit, I get minus n e to the minus n, and if I substitute 0, I simply get 0, and then it's plus because of the two negative signs, the integral from 0 to n of e to the negative x dx. So we get minus n e to the negative n plus e to the minus x over minus 1. Remember, I'm dividing by the derivative of the exponent from 0 up to n. So we get minus n into the minus n plus e to the minus n over negative 1 minus e to the minus 0 over negative 1, which gives minus n e to the minus n minus e to the minus n plus 1, which can be written as 1 minus brackets n plus 1, and we factor out the e to the minus n as required. In part D, we need to show that for Xiang's model, k is 99 to the nearest integer. So remember, we need to show that the integral from 0 to 4 of kx e to the minus x dx turns out to be 90, which is the total frequency, the 90 people included in the sample. So we can take out the k, and we've got k integral from 0 to 4 of x e to the minus x dx is equal to 90. And I will now use the established results. So we've got k, and we've got 1 minus the n plus 1, and in our case the n is 4. So 4 plus 1 e to the minus n, so e to the minus 4 is equal to 90. So we get that k is equal to 90 over 1 minus the 4 plus 1 e to the minus 4, which gives an answer of 99.0729, which gives 99 to the nearest integer as required. Now in part D, we need to estimate this probability using Thomas's model of a normal distribution. So I will simply go on my calculator once more and use the normal distribution function to find this probability. So I'm going to press menu, 7, normal CD, the lower is 10, the upper is 30, my sigma is 9.3, and my mu is 14.9. So this gives an answer of 0.6486. And then in II, we need to use Xiang's curve with equation y is 99x e to the minus x, and the answer to part C to determine this probability. So remember, we're trying to calculate the integral from 1 up to 3 of 99x e to the minus x dx. The reason I'm using 1 and 3 is because x is measured in tens of hours, so 10 hours means that x is 1, and 30 hours means that x is 3. I will take the 99 out, so 99, and the integral from 1 up to 3 of x e to the minus x dx. Remember, I need to use the answer to part C, and the answer to part C is involving an integral starting from 0 going up to n. So what I will do is I will write this as 99, the integral from 0 to 3 of x e to the minus x dx, minus 99, the integral from 0 to 1 of x e to the minus x dx. So I'm just saying that the interval from 1 up to 3 is written as the interval from 0 to 3 minus the interval from 0 to 1, so that I can use the established result from part C. So this is 99, and we've got 1 minus 3 plus 1 e to the negative 3 minus 99, and we've got 1 minus 1 plus 1 e to the minus 1. If I plug this on the calculator, I get 53.124. So it's 53.124 out of the total of 90. So the probability of 10 less than t less than 30 is equal to 53.124 over 90, which gives an answer of 0.5903. And finally, in part F, we've got the researcher deciding to use Xian's curve to model the probability of capital T being between A and B. And we need to state the limitation of this model. Well, if we briefly go back to the definition of the model here, we can see that x can attain values between 0 and 4. And since x is measured in tens of hours, this means that the model proposed by Xian can only allow for times of up to 40 hours. However, patients might stay for longer, and this is indeed a limitation for the proposed model.